Alright, so in this video I'm going to review the Section 8 in the recent assessment on the Advanced Mechanics section of Year 13. So let's get cracking straight away. So for a body performing simple harmonic motion, which one of the following statements is correct? So let's remember that for simple harmonic motion, acceleration is directly proportional to the negative of the displacement. That's the condition of SHM. So the maximum kinetic energy is directly proportional to the frequency. Well, you do have this equation like this, so Vmax is 2 pi Fa. Kinetic energy would be that squared, so it would be proportional to frequency squared, so that's not correct. Time for one oscillation is directly proportional to frequency. No, for SHM, you have this relationship there between the time period and the frequency. They're inversely proportional, so that's not correct. The speed at any instant is directly proportional to the displacement. No, it isn't. That's not a thing. The maximum acceleration is directly proportional to the amplitude. So there's another equation in your formula sheet. Amax is minus 2 pi f squared a. So yes, that's correct. So it would be D there. Alright, so moving on. So we've got a particle of mass 0.2 kilograms. Moves with simple harmonic motion of amplitude 2 times 10 to the minus 2. The total energy of the particle is 4 times 10 to the minus 5. What is the time period of the motion? Okay, so what we're going to do is we're going to use the Vmax equation, which is 2 pi Fa. So the kinetic energy, when it's at maximum speed, will be all of the energy. So it's going to be half mass 2 pi Fa all squared, which is equal to 4.0 times 10 to the minus 5. So when it's at maximum velocity, the equilibrium position, all of the energy will be in the form of kinetic energy, so we can equate those two. So let's put that into calculator. 4.0 times 10 to the minus 5 times by 2 to take the half across, divided by 0.2 takes the mass across, square root, divided by 2, divided by pi, divided by 2 times 10 to the minus 2, gives us a frequency of 0.159. And then remembering that time period is 1 over frequency, so let's do the 1 over that, and that's 6.28 blah blah blah, which is 2 pi. So that's going to be option number D there. Alright, let's continue. When a mass is suspended on a spring is displaced, the system oscillates with simple harmonic motion. Which of the following statements regarding the energy of the system is incorrect? Potential energy has a minimum value when the spring is fully compressed or fully extended. That's wrong. Potential energy is maximized when it's fully compressed or fully extended. So if you extend a spring, you're storing the energy as potential. So that statement here is not correct. But let's just check our answer. Kinetic energy has maximum value at the equilibrium position. That is true because velocity is maximized at the equilibrium position. The sum of the kinetic and potential energies at any time is constant. Yes, because the sum of total energy is always constant. Potential energy has a maximum value when the mass is at rest. So where the mass is at rest at either the when the spring is fully stretched or fully compressed. So yes, that's true. So it's going to be option A. That's going to be correct. Okay, so let's move on. Okay, so we've got a graph showing the variation in displacement with time for an object in SHM. Okay, so what's the maximum acceleration of the object? So first of all, we can pick up from this graph that A is equal to 10 times 10 to the minus 2. That's 0.1 meters. We can also pick up that the time period, the time for one full oscillation, is 2 seconds, which means the frequency is 0.5 hertz. So A is equal to minus 2 pi f all squared times A. So let's plug that in. So we do 0.5 times 2 times pi squared times 0.1 gives us 0.986 986 blah blah blah. So that's going to be option B there, and we'll actually get that at the points of maximum displacement, because we know the acceleration is directly proportional to displacement, so A will be maximum when displacement is maximum. Okay, a small body of mass m rests on a horizontal turntable at a distance r from the centre. If the maximum frictional force between the body and turntable is mg/2, what is the angular speed at which the body starts to slip? So what we've got is we've got a turntable, and we've got, this is the centre here, and we've got an object on it, which we're trying to get to go essentially in circular motion. Now, if something's in circular motion, that must mean there's a force acting towards the centre, and that's going to be the frictional force. So the centripetal force in this case is going to be mg/2, which will therefore be equal to m omega squared r. So the friction is the centripetal force, so that's what allows us to equate those two. So we can get rid of the m's, and we want to get omega by itself. So we take r over to the other side and square root, and so what we're looking at is option C there. Okay, so let's move on to the next one. Okay, so we've got a mass m attached to a spring as shown, and it's displaced downwards and oscillates with time period t. An identical spring is connected in series when the same mass is attached. What is the new time period? So let's first think about what the time period of a mass spring system is. So what's going to happen when we put springs in series is the spring constant is going to change. So in series, they follow a reciprocal rule, and they're both identical. So essentially we're going to end up with 2OK. So what's happened is the total is now k/2. So we've now got half. So when we put that into this fraction here, what we're going to end up with is 2 pi of 2m over k, and that's going to be root 2. So this is, we're calculating the t new, and that's root 2 times the old t there, which inserts option C for that one there. Okay. Yep, that's the last one on this page. Let's move on. Alright, so we've got a string passing through a smooth, thin tube. Masses m and m are attached at either end, and the tube is moved so that the mass travels in a horizontal circle of constant radius r and a constant speed of v. So it's going to be in circular motion. So essentially there needs to be a force acting towards the centre. So this is kind of going around in a circle like this. So there must be a force acting towards the centre, which is the tension. And we also know that the tension is going to be equal to mg, because that's the weight causing the tension there. So that's the setup. So what's going to be equal to m? So if it's in circular motion, essentially what we're going to find out is essentially we've got this relationship here. So if the tension, and therefore like this weight force big mg, is causing the centripetal force, that's why we can get this expression. And we want to calculate just m, so it's going to be m v squared over rg, which is option C there. Okay, so a small mass is placed at P on a horizontal disk, which has its center at O. The disk rotates anti-clockwise about a vertical axis through O with a constant angular speed. Okay, so what we're essentially going to try and do is P is going to try and stay on here. We want it to like, if it's not going to slip, essentially it's going to need to be in circular motion. So which one of the describes the force which keeps the mass at rest relative to the disk? So it's going to be at rest relative to the disk if the mass is also in circular motion and the same circular motion or the same angular speed as the disk. So in order for that to be a case, there must be a centripetal force acting towards the center or from P to O. So it's not going to be the weight of the mass because that's like acting into the page, so that's not towards the center. A frictional force from P to Q, that's not acting towards the center. A frictional force directed away from O is acting away from the center, so that's not the one you want. So it's going to be D, a frictional force directed towards the center or towards O. Okay, so with this next one, we've got a pendulum and a mass spring system with the same frequency on the surface of the Earth, and the pendulum and the system are taken down to a mine where the acceleration due to gravity is less. What happens to the frequency? So let's write down the equations for the frequency of the two scenarios. So we've got these two here. So you can see, looking at the mass spring system equation, there is no G in here, so that's not going to be affected, so we can eliminate anything that says otherwise. So we can get rid of those not relevant. So we can see here that if G it decreases because we get taken down a mine, you can see the frequency is going to decrease, so that's going to give us option D there. Okay. And final question on this one. So a model car moves in a circular path of radius 0.8 meters at an angular speed of pi over 2 radians per second. What is its displacement 6 seconds after passing P? So let's calculate its angular displacement. So that's going to be the angular speed times the time, 3 pi. So 3 pi is 1.5 revolutions, so if it starts here, it's going to go all the way around once, and then round to this point here. So it's gone from being at plus like 0.8 to minus 0.8, if you like, so it's changed by a factor of 1.6 meters there. And that concludes this part of the exam.